Prepare to embark in a captivating journey into the realm of Bernoulli's principle. In this discussion, we unravel the mysteries of fluid dynamics where air and liquid dance to the rhythm of this fundamental concept. Brace yourself for a thrilling exploration as we uncover the magic behind lift, airflow, and the unexpected wonders that Bernoulli's principles unveils in our everyday experiences. Remember, curiosity is the fuel that propels us forward. So let's join the vortex of Bernoulli's principle and emerge with a knowledge that soars. Get ready for a fluid adventure. So, good morning, everyone. Our topic for today is about the Bernoulli's principle. Are you all excited to learn? Well, I see. Now let's start. So, who among you here knows what is Bernoulli's principle? Anyone? Okay, that's correct. Thank you.
What is Bernoulli's principle?
Bernoulli's principle, named after the Swiss mathematician and physicist Daniel Bernoulli, who first formulated the principle in 1738. It is a fundamental concept in fluid dynamics that relates pressure, speed, and height. I have here an example. So, imagine blowing air horizontally underneath a sheet of paper. The air molecules move faster under the paper due to the narrow space, creating a low pressure zone there. On top, the air remains lower and exerts a higher pressure. This pressure difference pushes the paper upwards, shin bar defying gravity. That's Bernoulli's principle in action. Faster moving fluid experiences lower pressure, while slower moving fluid experiences high pressure. These principles play a role in many everyday phenomena, from airplanes' wings generating lift to the curve of a spinning ball in water. Now let's proceed to its theory statement. So increase in the speed of the fluid occurs simultaneously with a decrease in pressure and decrease in a fluid potential energy. In a horizontal pipe, the highest fluid pressure is in the section where the flow speed is the lowest, and the lowest pressure is at the section where the flow speed is the biggest. According to Bernoulli's principle, the Venturi tube is a specialized piece of equipment shaped like a funnel used to demonstrate and apply the principle that fluid speed and pressure are inversely proportional. So I have here an example. So the tube has a wide inlet where the fluid enters at a relatively low pressure and high pressure, while in the middle it is a narrow throat where the cross-sectional area of the tube is significantly reduced. As the fluid enters the throat, it forced to speed up due to smaller space. So according to Bernoulli's principle, this increase in speed causes a decrease in pressure at the throat. This is the key point to remember. Finally, the tube gradually widens back out towards the outlet, where the fluid slows down. As the speed decreases, the pressure also gradually recovers to its original value at the inlet. Bernoulli's principal theory equation: P1 plus 1 half PV1 squared plus PGH1 equals P2 plus 1 half PV2 squared plus PGH2, wherein SI units, P is the static pressure of fluid at the cross-section, ρ is the density of the flowing fluid, G is the acceleration due to gravity, V means velocity of fluid flow at the cross-section, H is the elevation head of the center of the cross-section with respect to a datum. Let's try answering this sample problem number 1. So, water enters a horizontal pipe of a non-uniform cross-section with a velocity of 0.6 meter per second and leaves the other end with velocity of 0.4 meter per second. At the first end, pressure of the water is 1,600 Newton meter squared. Calculate the pressure of water at the other end. Density of water is equals to 1,000 kilogram per cubic meter. So to get the answer, Bernoulli's equation for a horizontal pipe can be used to find the pressure at the second point of the pipe, which is 1 half PV1 squared plus P1 equals 1 half PV2 squared plus P2, where ρ is the density of water equals 1,000 kilogram per cubic meter. V1 is the velocity at first point equals 0.6 meter per second. P1 is the pressure at first point is equals to 1,600 Newton per meter squared. V2 is the velocity at second point, which is equals to 0.4 meter per second. So P2 is the pressure at the second point. So we will be solving the P2. So putting these values in the Bernoulli's equation, P1 is equals to 1 half times 1,000 times 0.6 squared plus 1,600 equals 1 half times 1,000 times 0.4 squared plus P2. So P2 is equals to 500 times 0.6 squared minus 0.4 squared plus 160. The answer is 1,700 Newton per meter squared. So the pressure of water at the other end of pipe is 1,700 Newton per meter squared. Now let's move forward to the applications of the Bernoulli's principle. So first example is the wing shape. So the curved shape of airplane wings is carefully designed to create a pressure difference between the top and bottom surf. Because of this curvature, the idea goes air traveling across the top of the wing moves faster than the air moving along the wing's bottom surface, which is flat. As air flows over the wing, it has to travel a longer distance over the curved top surface than the straighter bottom surface. This causes the air to speed up over the top, creating a region of lower pressure. So this pressure difference, known as lift, is what keeps airplane aloft. So the next application is the spray nozzles. It plays a significant role in Bernoulli's principle by utilizing it to achieve atomization, the process of breaking up a liquid into fine droplets or mist. So try to imagine in the nozzle of a perfume bottle or paint sprayer, or even a water sprayer. As a trigger is pressed, liquid is forced through the small opening. The narrow opening acts like a venturi throat, causing the liquid to speed up. This increase in speed, again, thanks to Bernoulli's principle, leads to a pressure drop at the nozzle tip. This low pressure draws air into the liquid stream, breaking it up into fine droplets or mist, creating an efficient spraying mechanism. So next we have the hovercraft. So it utilizes this principle to achieve lift and glide effortlessly over surfaces. So try to imagine a vehicle gliding effortlessly over water and land. A hovercraft uses powerful fans to push air downwards, creating a high pressure air cushion beneath itself. So this pressurized air acts like a giant pillow pushing against the ground or water, generating an upward force that lifts the hovercraft and allows it to float in the water. So this is essentially Bernoulli's principle in action on a large scale. And lastly, we have curved ball baseball. So the power of curved ball lies in the beautiful interplay between speed, airflow, and Bernoulli's principle. Here's the breakdown. So when a pitcher throws a curveball, they impart a strong spin on the ball, usually clockwise if thrown to a right-handed batter. This spinning motion drags the air around the ball, creating different air speeds on either side. On the top side of the ball, where the spin pushes the air forward, the airflow speeds up. Conversely, on the bottom side, where the spin pushes the air backward, the airflow slows down. In essence, the curved ball defies gravity not through magic but through the clever manipulation of air pressure using spin. It's a fascinating example of how physics can be applied to create truly mesmerizing feats in the worlds of sport. So the wings of an airplane, so elegantly shaped and angled, embody the spirit of Bernoulli's principle. They not only defy gravity but also carry us to distant lands, expanding our horizons and perspectives. This principle then becomes a metaphor for the wings of knowledge, urging us to rise above the limitations of the familiar and seek understanding in the boundless skies of inquiry. As Leonardo da Vinci proclaimed, knowledge is power. Armed with the insights of Bernoulli, we can soar towards new heights of wisdom, conquering not just physical realms, but also the limitations of our own world. So, I guess that concludes my discussion. I hope you learned something. Thank you.